Finally, I'm gonna go over problem two, which is, I think, without a doubt, the hardest problem in the set. So for problem two, so Bessie is jumping on a number line, and she has two types of and on her number line there are jump pads and there are targets, and for each target there's a value v, where if Bessie's current velocity is greater than or equal to v, she will break the target. And on each jump pad, Bessie, there's a value. I forgot what they said it was. It's just v. Bessie will increase her velocity by v, and then she'll reverse her direction. And then Bessie the cow initially starts so Bessie the cow initially is at, oh yeah, and then when her velocity is v, she will move forward v steps in a particular direction. For instance, if Bessie the cow is currently on position one, my pen is broken again. Okay, if Bessie the cow is currently on position one with a velocity of 2, and she is facing to the right. Uh, then after one jump, she's going to end up at position 3. Or she will increase, oh, what happened just now? She'll increase her velocity, or she'll increase her position by the amount of her velocity in a specific direction. And then say at position 3, her velocity somehow changed to be 3, and she also switched directions. And now she is facing to the left. She will now jump to 0, which would be 3 minus 3. So, yeah. Okay, so Bessie the cow starts off initially at she's initially at position S with a velocity of 1, and then facing the right. Facing right. And the question is, after some indefinite amount of time, what is the total number of targets Bessie the cow will break? So there's a couple ways to think about this problem, but the most basic is to just imagine simulating the process where you keep track of Bessie's position, her velocity, and her direction. And you just simulate this process some amount of time, for like, I don't know, just for a while. And so there's a couple of important things. The first thing is that if Bessie the cow ever ends up at the same position, velocity, and direction that she has already been at before, she will end up in a loop forever. And this makes sense because if Bessie is currently at some state, my pen is broken. Oh, I don't know why. Okay, if Bessie the cow is currently at some state, right, she'll move forward to another state. But if she ever finds her way back to the same state of having the same position, velocity, and direction, she's stuck in a loop because she'll move forward again, and eventually she'll make her way back. So if she ever ends up at the same position, velocity, or direction, Bessie the cow cannot break any more targets because she would have broken everything already, and now she's stuck in the same loop forever. Similarly, if Bessie's position is ever less than 1 or greater than n, she also will no longer break any more targets because once she's past the interval where from 1 to n where there exists jump pads, she'll never change her direction. And if she ever goes past 1, her direction has to be facing the left, and she'll have to bounce off towards negative infinity forever. And the same is true if she ever ends up at a position strictly greater than n. So now we know when just when to terminate. And now the question is, what's the maximum number of states Bessie can be in, where state is defined as position, velocity, and direction? How many states can Bessie the cow be in? Because if she can be, because preemptively, it looks like she could be in n squared states, where her position is everything from 1 to n, and her velocity is everything from 1 to n, and also two directions. And if this is the case, then this algorithm will actually be too slow. But I'm going to show that this is actually not the case, and Bessie actually is in at most O of n log n states. So okay. And then I'm gonna erase some of the other stuff. And the rough idea of the solution is this. So let's say Bessie has her velocity currently equal to v, and then she's facing some direction. Let's just say she's all right. Yeah, so she has a fixed velocity and a fixed direction. Uh, um, my pen is having a seizure. Okay, she has a fixed velocity and a fixed direction. And I claim that Bessie can be in at most n over v states with the n over v positions with this velocity in this direction. And this is how it works. So first off, note that if Bessie the cow ever switches her direction, her velocity will end up strictly greater than what it was initially. And this is true because to switch direction, she has to land on a jump pad. And if she lands on a jump pad, her velocity will increase. Wait. No, 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 no. Sorry. Let me take that back. All right. Yes, that was not what I meant to say. All right, so I forgot that the value could be 0. Yeah. All right, so Bessie the cow for fixed velocity and fixed direction. So first off, her velocity is it's non-decreasing. Yeah. It can't end up at some value strictly less than what it was initially, because her velocity will only ever increase or stay the same, right? And what this means is that Bessie the cow is going to jump forward v here, and then jump forward v again, and so on and so forth, until eventually her next jump will have to exceed n. Or it'll be, yeah, or her next jump will eventually have to exceed n, or similarly, it'll eventually have to be less than 1. And basically, she can't she can only visit these particular jumps that are of size that are of distance v from where she is currently, and she can't really shift between that, because she can jump yeah, so let's I don't know how. So like, yes, you can jump between different indices that have like the same value mod v, but she can't actually change her value mod that particular v, because to do so she'd have to increase her velocity. And changing the direction, she'll still end up in the same set of indices, and there's at most n over v of them. So you can show that for fixed v, Bessie can be in no more than O of n over v states, n over v positions. And when you sum this up over all the v, you end up with a sum that looks like this. It's like sum of sum of n over v, v goes from 1 to n. And if you know where this is going, it's that this sum is actually it's called the harmonic sequence. And this is the same thing as if you have n equals one, two. So you take you extract the n of one over v, and it's a well-known fact that the sum of all of the fractions or like reciprocals from one to n is approximately log n. The proof for this, I guess you can Google it, and there's another pretty nice way to do it by grouping powers of two. But this sum is log n. So the result is that Bessie the cow can be in O of n log n different states. And what this means is that we can actually just simulate the process until she either visits the same state twice or jumps off the map. Or it jumps off the map in the sense of like having a position less than one or greater than n. So what we can do is Silver should start in a couple of minutes. So what we can do is we can keep a an STD set of an STD set where we store our current direction, position, and velocity. And all right, yeah, oh, my pen had to see here again. Here. We can store a set of all the directions, positions, and velocities we visited so far. And if we ever visit the same state twice, we can break immediately. Otherwise, we simulate what happens at that step. So we will either update our velocity with the current we'll either update if we land on a jump pad, we'll change our velocity and direction and position afterwards. And if we land on a target, we'll check whether or not the target has been broken. And if not, we'll see if we can break that particular target. And the n complexity will end up being O of n log squared n. Oops, squared n. Yeah. And that's the solution for bronze P2. Yeah, that would be all. Are there any other questions? And then I'll send the code for the problems in a second.